Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, everyone. Today is 2025 year, and we reached lecture number 7 for subject of advanced artificial intelligence for the Department of Software Master Degree. We continue with the previous lecture. We focus about chapter 4 in this book, our first book, and we reached implementing best-first search. The best-first search algorithm selects the most promising states on the open for further expansion. As we remember the best-first search, we focus about two factors or two sets used in solving the algorithm of the best search for the depth or breadth search strategy, where open contain the nodes where we visited but we not explore it till now. That means open contain all the nodes we want to explore it and expand it in the future. However, as it's using heuristics that may prove erroneous, it does not abandon all other states but maintains them all open. Best-first search focused upon about selecting or ordering the evaluation function in the open list, which we select or put the best one that has best value of evaluation function in the first position, and so on. That means we select the best one, which means have the best evaluation function. In the event heuristic leads the search down path the proves incorrect, the algorithm will eventually retrieves some previously generated next best state from the open list and shifts its focus to another part of the space. After the children of the states B were found to have poor heuristic evaluation, that means failed, where we select nodes B and failed in selection, then the search shifted its focus to state C. That means select another node, which means C. The children of P were kept on open. That means when we leave open, leave P nodes, the children of the P will were kept in the open list and reordered. The ordering depends on the best of evaluation function in case the algorithm needed to return to them later. The open list supports packet tracking. Now, packet tracking algorithm or packet tracking strategy will apply in this algorithm and represented in the open list from path that fails to produce a goal. For example, the figure below shows starts goal state for 8 puzzles along with the first 3 statements rated in the search. Now, this is the starts. This node represents the initial state and represents the start of the search problem, and this is represent the goal which we want to reach it. And from the start we branch it for 3 branches. The first branch will we move because this game depends on the moving of the black tile, and this movement either be both down, left, right. Now in this state where we start as like this fashion, We see the black tiles. We have three options to movement. The first movement, either I move it for the left, this like this, here, and either it will be moved up like this, here, or right like this. This is all possible. You can use it and continue. This is figure represents the state space or representation of the state space of the problem of the item. Now, let's implement the evaluation function for this figure. This is example. The simple series count the tiles out of places in each stage when compared to the goal. This is intuitively appealing because it would seem that all else being equal, the stage that had the fewest tiles out of places is probably closer to the desired goal, like this. Here, when we begin to research about the goal and this problem, if we use the traditional search, that's blind, maybe the search will try all possibles, and it will cause time complexity, and the search will be complex. But maybe I use the heuristic, and as we mentioned in the previous lecture, the heuristics means that I put guide to guide the problem solver to select the suitable price. Now, in your opinion, how can I use the function can be used to evaluate this or guide the problem solver to select suitable one? One of them, I can use the number of tiles that out of real place. For example, this goal and this initial states. Now, let's count the number of tiles that is not in the correct place. For example, here I found 1, but what I found 2, because the goal here 1 and here's 1. This is out of place code. Now 2 or this tile haven't the correct answer, and this is 1. Now here 2 and here 8. This is incorrect. Now 2. Here 3 and 3. This is correct. Here 8 and 1. 4. And this is 3. Now 1, 2, 3, 4. This is 4 places. Now we count which one we need. Count the places or the tiles that is out of places. Now 1, 2, 3, 4, 5. This is 5. And this 1, 2, 3, 3. This is 3. And this 1, 2, 3, 4, 5. This is lowest value because this is 4, 5, and 5, and this is 3. This is nearest for the goal. I can use this value as evaluation function to select the best selection or best price. Now this is price lead us to the goal with the fewest error or the fewest fault. Now we select this. This is called heuristic function or evaluative function. However, this heuristic does not use all of the information available in the above configuration. Now, this is method despite I regard this is the first one, but this is not the first solution. Why? Because this is not contained all the information that guide us to select the first one. Now, I'm looking for another manner or method to increase the probability of the selected first one. However, this heuristic does not use all of the information available in the bottom because it does not take into account the distance the tiles must be moved. Now, look at this. The distance of the movement is up to only one tile. Okay? And this exchange, only this for this place, this one place, and the two one place. But 8, how many places that can visit to reach this source place? Now, this is here. Must move it here, this one place, and this put in here, become 2 places. Now, I will put another factor to evaluate this function by putting the distance for each tiles when I move it until I reach the correct position that represent the correct of all the problem. Now, I get 2 factors. The first one, the number of tiles out of places. And the another factor I put it to the solution is the number of each place or each tiles, the number of movements that I can make me to reach the final places. And called is the distance. A pattern heuristic would sum all the distances by which the tiles are out of places, one for each square a tile must be moved to reach its position in the goal set. Now, the first one is the summations of these 2 factors. The first one, the number of tiles out of places, plus the number of distance that when I moving the particular tiles until I reach the correct place. 2 factors this. Now, both of these heuristics can be criticized for failing to now acknowledge the difficulty of tiles reversals. That is, if the 2 tiles are next to each other and the goal requires their being in opposite locations. Now, there is another factor. This represents the inversing of the movement. When 2 tiles, for example, like this, when there is 2 tiles, but each one occur in the place that belong to other one or the opponent one. For example, here must be 1 and here must be 2, but here I found 2 and here is 1. I must exchange them. But how I can this exchange this happen? This happens by moving one of them for a particular place, this one movement, and I put the first one in this places, these 2 movements, and then I return the other for this place. Now, for exchanging of them, I need at least 3 movements. Moving of this, moving of this one, and moving this for a particular place, and then returning this for this place. Now I need 3 movements. This must account or considered in the searching problem. Because if I counting the number of tiles out of places. For example, now here 2. But is different from another problem. For example, this and this. This only to change. Because the pair here, I want to 3, at least 3 movements. Now this is what we considered in the problem solution. Thus, I get 3 factors. The first one, the number of tiles that out of places. That means the number of tiles that have wrong places. This one. 2, the number or the distance, the count of the distance for each tiles. For example, now 1 or, for example, if I have 4 here, for example, how many places I visited where to put 4 here? This is number of the distance. And the other things, the number of opposites places. Now I get 3 factors to evaluating the evaluation function. And I will put it in these examples. This figure will illustrate the calculations of each evaluation function for these 3 factors. The first one is tiles of the out of place. That represent the number of tiles out of places. And this one, the sums of the distance. And this one is the number of reversal location. Now, for example, here, this figure or this fashion, the number of out of place tiles out of places here, that's 5. Let's count it, each one. This one, 2, 3, 4, and 5. Because 7 here. 1, 2, 3, 4, 5. This is 5. And the number of sum of distance out of a place. The number of sum. For example, the distance here, this is 1. Because I put here. This one. And this, only 1. Only place. Now 2. The distance is 2. But 8. I move it here, this is 1, and move from here to here, 2. Now, 2 plus 2, 4. And 6 need 1. Now 5. 7 here, this one, 5 plus 1 is 6. Thus, the sum of the distance out of a place is 6. And are there any 2 tiles inverser or reverser? No, there is no problem. Thus, the number of inverser 0. And now look this example. The number of out of a place, tiles out of a place, this 1, and this 2, and this is 3. Only 3. Thus, the number is 3. But the distance, this is only 1, and this is only 1. But this need 2 movements. 2 and 2 plus 2, 4. The number is 4. And there is no 2 tiles that has opposites or reversal location. There is no one. And this is 0. No reversal. So this fashion is 1 and 2, 3, 4, 5. Because this is 0. The number is tile of out of place 5. The evaluation function for the distance of the out of place is 5. And the number of the tiles or the distance of the tiles that out of the places here. Now, this 1 and this 1 and this 1 and this 1 and this is 2. 4 plus 2 would be 6. This is 6. Because this 2 and 2, 4. And this is 2. 2 plus 4 would be 6. The sum is 6. And also, there is no two tiles have reverse application. No, this is 0. If two states have the same or nearly the same heuristic evaluation, if we get the two nodes have the same evaluation function, it is generally preferable to examine the state that is next to the root state of the graph. In the graph, for example, this is graph. If I get two states have the same evaluation function, which one I would select? I will select the one that have the shortest path from the start state to this state. Now, the same heuristic, if you have same heuristic, it is generally preferred to examine the state of nearest to the root states. Nearest one, nearest path. This state would have a greater probability of being on the shortest path to the goal. I select shortest path because the best algorithms that have the best time complexity, and the shortest path will implement the shortest time complexity or the best time complexity. The distance from the starting state to is the same distance can be measured by maintaining depth count for each state. Depth counts. Now, the depth counts will be represent the distance that need to do movement. These depth measures can be added to the heuristic evaluation of each state to be a search in favor of states found shown in the graph. This makes our evaluation function f, and this f functions will be represented by the summing of the two factors, gn and plus hn. And what's the meaning of gn and the hn? Gn's measure the actual length of the depth from the state n to the start states. That's measure of the depth. That means the number of level in the graph. This is mean gn. hn represents the evaluation function. hn is the heuristic estimate of the distance from the state n to goal. hn represents the value of the function that we represented for the evaluation function. Now in this, how we calculate the Fn? Before I calculate the Fn, I must get two values of Gn and values of the Hn. Gn represents the number of levels. The first one have Gn is 0 because the level 0. And the second one is 1. The Gn equal to 1 because this is level 1 or the first level. And second level and third also. But the Hn here will represent the number of tiles of the places. Here, Hn 1, 2, 3, 4, 5. And here, now, Fn for this evaluation function for this node will represent the summation of the Hn, and Hn is 5 plus Gn is 1. This function will be 6. Fn will be 6. Gn will be ensure the accuracy of the search. How is it doing? For example, Gn here 1, but the number of evaluation function is 5. If we in another level and Gn, for example, Gn is 5, for example, 5, and Hn also 5. Which one is with the best? This is best because this is the nearest for the goal state or the root states. Now Gn will control us to select the best one depending on the Gn, because the Gn represents the number that refer to the nearest of the initial states. Now figure out this figure illustrate the first or the full past search. Full past search of the hypothetical graph by using the evaluation function f function, where each state will be labeled with the letter, and its heuristic search or heuristic function represented by the fn and represented by the summing of the gn of the hn and hn. Gn and hn, after adding of this, will get fn for each one, and the number at top of each node or figure indicates the order in which it was taken of the open list. Now this one, that means it is the first one take off from open list, and this two number represent this node will be the second node will be take off open, and 3 represent this node will be the third node that will be removed or take off from the open list, and so on. Thus, this number represents the number of this node will be removed, or order of this node will be removed from the open list. And other states, example, P and D and G and H, there is no label. Which means of this no label? For example, this node and this node, this node, this. There is no label. There is no number. But this is still in the open list. These nodes is found in the open list. But this means these nodes not visited yet, and this will be kept in the open. And this number, after I remove it from open, and will put in the closed list. If I ask which one of them, all of them, will put in the, or they will found in the closed, these numbers, this node that's numbered will be found in the closed list, because when I visit it and I traverse it, go to the another nodes, it will be removed from open and put to the closed list. So now let's complete the implementation of the heuristic evaluation function, and this figure and these represent the steps of the implementing or devising the searching algorithm in the first algorithm. Now the first iteration, because this is for 8 iterations. The first iterations, the value of open and the closed will begin. The first one, open, will be A4. Here, A4. Now, A and the evaluation function of the A is 4. How I get the A or the value of the evaluation function 4? How I can get it? Because the evaluation function represents the number of G plus H. H is 3. 1, 2, 3. Fn would be 4. And the closed is empty. Now, the second iteration, I must remove A from the open and get its children, put their children after arranging it according to its value evaluation function, put it in the closed, in the open, and put the removed node in the closed node. Now, open will be the children of the A will be B, C, D. Put where? In the open state. But I arrange it according to its evaluation function. The first one will be the C because have fewest value. That means 4, and put in the first location, C4. And the other, B and D, I will select B because B and D equal value. But as remember, when I countered with 2 nodes with the same value, I will select the first one. I reach it. The first one, this. I will select it. And after this, select D here. Now go C, B, D. And I will put it in the closed. This 2 or the second iteration. Now go to the third iteration. Watch. And what I will doing? I will remove the first one from the open list. Now, open list. Which one is the first one? The C. We'll remove it and put it where? In the closed. Will be in the closed now. C, put here. And get the children of the C. Children of the C, this E, F, G. And put, after arranging its value, put in the open. Now, here. A, F, and G. G becomes the last one because the same value of the B and D. And last one. Now, the ordering, E will become the first one and F will be first one. Now, the fourth iteration, I must remove the first one. That means E. Where is E? Here. Remove it. And put it in the closed. Here, put it in the closed. And I get the children of the E. Children of the E. State H and I. And rearranging it. After arranging it, where will it go? I will be the last one. This is I. And H will be the second. Before it is F5. That means 5. Because now F become has priority more than H and I. Because this is well put in the first position. And now I will remove in the fifth iteration. I will remove the first one in the open, and the first one is F5. F5 will be put on the closed here. F5. And get the children of the F. Children, that's mean state J and state K. Put after arranging it, because it's half 5 and it's 7. Arranging it like this. J will become the first one. J, that means this node. Now, remove in the second or the sixth iteration, I will remove J from the open here and put in the open. This is J. And the children of the J is in state I. And the error D will become I, the first one. And so on. This is the what I discussed in these slides. because these steps, what I illustrated in the previous, or the same talk I taught in the previous slide. Now we'll represent for the third iteration. After third iteration, I will get this figure, because the dark one represent is the closed list, and the light one represent the open list. The first one, A1 or A4, will be with the dark color, or the black or the white color. The first one. Second iteration, I will get, or I put A in the closed, that means will be dark, and these three will be light. After two iterations, I will get this is the black, and I will get it dark or light, these, and these, and these only. After three iterations, I will get the open only these and this and these, and the closed will be these. Now, to summarization of this representation of the implementation of the heuristic search. The first one, operational state generates children of the states currently under examination. Each new state is checked to see whether it has occurred before, is either open or closed, thereby preventing loops. And third, each state n is given an f value. Each one have n value. This f value obtained by summation of the h value with the g value. The h value guides search toward heuristically promising states, while the g value can prevent search from persisting indefinitely on the fruitless path. States on open nodes in the open list are sorted by the f value. Thus, nodes arranged according to its value, f value, by keeping all states on open until they are examined or goal is found. The algorithm recovers from the dead end. And lastly, as an implementation of point, the algorithm's efficiency can be improved through maintenance of open and the closed list, perhaps as helps the leaf tree. Now, the purpose of these algorithms is to maintaining two lists, open and closed. This is the main purpose of this algorithm. Now, let's go implement the heuristic systems or the heuristic search in the experts systems. For example, 8 puzzles are ideal vehicles for exploring the designs and behavior of heuristic search algorithm for number of reasons. The first one, the first space are large enough to require heuristic pruning. Now, this is mean 8 puzzles. Why we select 8 puzzle examples to illustrate the heuristic search? Why we select the 8 puzzles? Because 8 puzzles have space large enough to represent or to implement the pruning in the heuristic. This first one. The second, all the games or the most the games are complex enough to suggest rich variety of heuristic evaluation comparisons and analysis. Because this one, the simplest one of all the games that can I reach the heuristic functions and its simplicity to evaluating function or to implement the evaluating function. Thus, the role is heuristics, and the problem solver should try to account for this uncertainty. And that will be the most factor that representing this, why we are selecting these examples as a puzzle. We could take an additional factor such as the age of the investor. Yeah. Sorry, this is 3. Games generally do not involve complex representational issues. A simple node for the state space is just a poor descriptions and usually can be captured in straightforward fashion. This allows researchers to focus on the behavior of the heuristic rather than the problems of the knowledge representations. Now, this is one of the other problem or the factor that we can be, make us to select or to choose these examples of 8 puzzles, because the complexity of these games is somewhat is the best one in complexity from other games in the representing the state space. Because in this example, for example, in these examples, the designer will not focus its attention to representing other things for the problem, and he will focus about only this problem, because the other problem, for example, chess or the advising of the financial advisor, will maybe will looking for representing other things and make the problem more complex than things. And because each node of the state space has a common representations, a single heuristic may be applied throughout the search space. This contrasts with the system with the financial advisor. Now, the other things, this problem of the 8 puzzle maybe have one factor of the evaluation factors, that he looking for the number of tiles of in this example, for example. But another example, and that's represents financial advisor, maybe the tool or the choosing for the selecting for a particular solution depend not only on the decision rule, maybe depend on other factors. For example here, this rule, for example, when he investment for stocks, why? Because the saving account adequate and income adequate. But sometimes maybe he saving account adequate and income is adequate also, but he may investment either combination or saving account. Why? Because the environment that we individual one living in particular environment make it attention to go this decision. For example, his age or the security state of the country, he make decision not put their money in the stocks, maybe put in an account bank. Thus, for example, a rule says that an individual with adequate saving and income should invest in the stocks. It is possible that such individual may prepare a security of the combination strategy for even the placing all investment money in saving. Thus, the role is heuristic and the problem solver should try to account for this uncertainty. Now, this is another factor called uncertainty. uncertainty must put with the evaluation function in his problem, and this make the problem more complex to solve. We kept the additional factors such as investors of the investors and the long-term perspective of the security and advancement in the investors' professions into account to make the rules more informed and capable of final distinctions. These another factors will be added with the other factors for selecting the evaluation functions of the system. However, this does not change the fundamental heuristics nature of the financial advice. For example, one way in which expert systems have addressed these issues is attach a numeric weight called confidence measure or certainty factor. Now, if we to solve this problem of the advisor, financial advisor, the evaluation functions will have, in addition to these factors I mentioned in the previous slide, I must have or put another factor called confidence measure or certainty factor, and this is represented by number. This number represents the probability of the fail or the correctness to get the results. And this may be number will be ranged from 0 and 1. 1 that means represent the certainty is perfect, and that means 1000%. When I get 1, and 0 that means 0%. That means this is exactly failed. Each rule conclusion is given a confidence measure, say real number between -1 and 1, or 0 and 1. -1 that means exactly failed, and 1 that means full succeed, with 1 corresponding certainty true, and -1 to defined value of false. That means this false and this is true. And the values between them, and the between reflects varying confidence in the conclusions. For example, the preceding clause may be given a confidence of say 0.8. What's the meaning of this? This 0.8 means the value between -1 and 1. But 0.8 near for 1. That means this is near to the succeed more than fail, reflecting a small probability that it may not be correct. Other conclusion may be drawn with the different confidence weights. For example, saving accounts adequate and income inadequate imply investment stocks with certainty confidence of 0.8. And another rule, for example, saving account will be adequate and income will be adequate implies investment combination. That means the investment will be combination with certainty of the 0.5. And another one, saving account is adequate and income is adequate. That implies investment will be savings with confidence 0.1. That means I will select investment savings, but near to the fail. This all reflects the common investment advice that also an individual with the adequate saving and income would be most strongly advised to invest in stocks. There is some possibility that a combination strategy should be preferred, and slight chance that they won't continue investing. Now there is 3 words that will be encountered when you reading articles about the heuristics. These three words, this admissibility and monotonicity and informativeness. The meaning of the admissibility means when a heuristic that finds the shortest path to a goal without whenever exists are said to be admissible. That means admissible when I using the heuristic and I get the search path that reach us to the goal. Now this search will call admissible. And informativeness, we may want to ask whether any pattern heuristics are available. For example, there is many possible paths. There is more than one path to reach us to the goal. And I ask which one is the best. Here is the informativeness. If I get the answer for to select the best one, now called is informativeness. Now, monotonicity, if there is many branches that get the best solution or the goal, but I want to select best one. The best one is monotonicity. When a state is discovered by using heuristic search, is there any guarantee? There is guarantee that the same state will not be found later in the search at the cheaper cost. Are there any guarantee that guarantees us after I select one path reach up to the goal? Are there any guarantee there is no paths that reach us to the same selection, the same goal with the fewest cost or the best solution with the few complexity? This is called the monotonicity. Monotonicity that guarantee there is no solution based on I get of this now. Only this is the person. This is the best search. Now, with detail, what is the admissibility? A search algorithm is admissible if it is guaranteed to find minimal path to solution whenever such a path exists. For example, breadth-based search is an admissible search strategy. Why? Breadth-based. Why is breadth-based is admissible? Because it looks at every state at level n of the graph before considering any state at the level n plus 1. Now, the breadth first, because this is visit each node in this level. For example, I now looking in the level n. And I will look for each one or each node in the level n before I go to the level n plus 1. That means when I level n and I'm looking for all the nodes here, that means I get the best one of the distance from the initial states for these nodes. And this will be guaranteed the admissible, get the shortcut path. Any goal nodes are found along the shortest possible path. Using the evaluation function fn equal gn plus hn, we may characterize the class of the admissible heuristic search strategy. If n is node in the state space graph, gn measures the depth at which that state has been found in the graph, and hn is the heuristic estimate of the distance from n to goal n. In this case, we will calculate fn estimates the total cost of the path from the start state to end to the goal state. Now we're looking about the F star. F star represents the actual function or the value function for the best shortcut path or the best solution. In thermal properties of invisible, heuristic we defines an evaluation function F stars, that's represent F stars equal G stars n plus H star n, where G n or G stars n cost the shortcut path from the start node n, and H stars returns the actual cost of the shortest path from n to the goal start. And it follows that F stars is the actual cost of the optimal path from a start node to the goal node that passes through node n, where we employ best first search with the evaluation function F star, because F star represents the actual value of the function for the best solution. F star, F value for the best solution. The resulting search strategy is admissible because it's a guarantee for selecting the shortcut path. It's called admissible. Now, Gn greater than or equal G stars, these are equal only if the graph search have discovered the optimal path to state S. Similarly, we replace H star n with the Hn heuristic estimates of the minimal cost to goal states. Also, we may not compute H star. It is often possible to determine whether or not the heuristic estimate of Hn is bounded from above by H star n, and it is always less than or equal to the cost of the minimal paths if the algorithm A uses evaluation function of the which H n H star n. It is called algorithm A star algorithm. Now, the definition of admissibility definitions algorithms A, admissibility, and algorithm A stars. Consider the evaluation function Fn plus Hn, where n is the states encountered in the search, and Gn is the cost of n from the start state, and Hn is the estimated or heuristic estimated of the cost of the goal from the end goal. If this evaluation function is used with the first search algorithm in the section 4.1, the result is called algorithm A. A search algorithm is admissible if for any graph it always terminates in the optimal solution path whenever path from the start to goal state is exist, and if algorithm A is used with the evaluation function with the Hn is less than or equal to the cost of the minimal path from n to the goal, now the resulting search algorithm is called algorithm A stars. It is now possible to state probability of A star algorithm. All A stars algorithms are admissible. Now this is the definition of the admissible strategy. Now the other words is the monotonicity. Recall that definition A stars algorithm did not require the Gn equal G star n. This means the admissible heuristic may initially reach no goal states along optimal paths as long as the algorithm eventually finds an optimal path to all states on the path to a goal. It is natural to ask this question. Ask if there are heuristics that are locally admissible that consequently find the minimal path to each state they encounter in search. This probability is called monotonicity. Now the definition of the monotonicity, definition, heuristic function H is monotone if either for all states Nj, Ni and Nj where Nj is descendant of Ni. That means H and I subtract from H and J less than or equal cost of Ni and Nj. Where cost of Nj is the actual cost, number of moves of going from state Ni to the Nj. And the other term, the heuristic evaluation of the goal state is 0 or H of goal equals 0. Now, in other words, informed heuristics. The final issues of these subsections compares two heuristics approach to find the minimal path and its definition of the informedness for the two A stars, H1 and H2, because the H is the evaluation function of the estimated function. If H1 for this n, for this node called n, less and equal to the H2n for all states in n search space, the heuristic H2 is said to be more informed than H1. Now, for example of this, the comparisons of state space search using heuristic search with the space searched by breadth first. The portion, now this portion of the graph search heuristically is shaded. The optimal solution path is notable. Heuristic uses Fn equal Gn plus Hn, where Hn is the tiles out of places, and this is figure. Now we will implement using of the heuristics in the games, and there is 3 examples. The minimax procedures on executively searchable graph and minimaxing to fixed plan, and the alpha beta procedure. Now we will represent, or we will illustrate the minimax procedure. Minimax procedure for exclusively searchable graph. Games has always been an important applications area for heuristic algorithm, because the games, the best example to illustrate this heuristic search. For example, 2 persons are more complicated than simple person because of existence of hostiles and essentially unpredictable opponents. Because when you play with the computer, it's different from when playing 2 persons. When you the playing of the one player, there is no opponents and there is no probability of the movement of the other opponents. But when we playing of the 2 persons, the first one will looking for the weak points of the opponents, and the opponents try to solve the weak points that I find, and to try to solve this weak point. For example, when I playing with the another or the opponent person in the chess game, when I moving the particular piece and I want to kill him with the rock. Now I'm looking for the winning and maximize the probability to get this winning, maximize. But the opponent, when I moving this piece, try to minimize maximize, to minimize the dangerous about the rock. And this fashion with the present competitive between the player and his opponents, and it's more complex than one player. Now, 2% depths are more complicated than simple puzzles because of the existence of the hostels and essentially unpredictable opponent. Thus, they provide some interesting opportunities for developing heuristics as well as greater difficulties in developing search algorithms. First, we consider games whose state space is small enough exhaustively searched because only a portion of the state space can be guaranteed, and searched the game player must use heuristic to guide play along path to winning state. Now let's go to the simple games of the name game. Name game, if someone not know about the or don't have information about name game, I have some pools, for example, either odd or even, and there is two players. The first one will divide these pools for two sub pieces, and when we reach the next level or the another opponent will try to subdivide these tools until they reach the someone, the first one. If we reach, we cannot divide these some pieces, that will be failed. To play these games, a number of tokens are placed on the table between two opponents. At each move, the player must divide a pile of the token into two non-empty piles. Non-empty piles of different sizes. Thus, for example, 6 tokens may be divided into piles of 5 and 1 or 4 and 2, but not 3 and 3. If I get 6 piles, I will divide it either or 2 and 4 or 1 and 5, but not allowed to divide it to equally size. That means 3 and 3. The first player who can no longer makes a move loses the game. For example, the opponent in a game are referred to mini and max. Now, the first one is the mini max. First one. For example, this 7 piles. The first one tried to maximize his opportunity to the winning the game. For example, either 6-1 or 5-2 or 4-3. That's opponent, and this is, for example, me. Max is me, and this is another opponent. Or this is first player and this is second player. First player, for the second player, I want to maximize. Now, the other player try to minimize the maximum of the another player. That's meaning opponents try to minimize the maximum of the first player. For example, here, where I select, for example, I select 6.3, 6 and 2, and that's 2 groups. He will try to minimize. How will he minimize? He will divide 5-1 or 4-2 and 1. And Maybe here will be 3, 2, and 2. Or when I select 4, 3, he will select 3, 3, 1. All this will minimize the getting the marks. Now, from these, I will take another try to maximize. If he select 5, 1, 1, I will select 4, 1, 1, 1 to maximize my winning. Or 3, 2, 1, 1, or 2, 2, 2, 1. All these try to maximizing or for maximizing my winning. Now, when he will opponent will play, try to minimize this and try to this too. After that, I will select this because this is cannot or possible. I will select this. This will be possible to win. And if I select this, he will win. Now I will select these to maximize the selection. And this is this figure where the heuristic is HN. The heuristic is EN, which equal MN, that's maximize, minus opponent N. And MN represents the total of my possible winning lines, and ON representing this like this, representing ON total opponents possible winning lines, and EN is the total evaluation for states N. For example, here X has 6 possible win paths, and O that means opponents, and X that means me, or the first person, or first player. First player has 6 possible win, and O has 5 possible win. The EN, that's in mean estimation function 1. If this estimation function will be 2 minus 2, and in this fashion estimation function will be 1. Now the first one maximize is 1. Maximum will be 1, and maximum will be minus 1 and minus 2. Now I will select this. And the same things, marks 1 and this is 0. If I select this one, and this will be select 1. This is either this or this, because the maximum is 1. Now this is 1, and this is choice. This is exactly what I lost the game, or the fail, and this is fail, and this is fail, and this is fail. Thus, I will select max 1 to win the game. Now, the chapter 6, holding control algorithm for state space search. Recursive search. Recursive procedure consists of recursive state. The procedure called itself to repeat sequence of actions. And in addition to the recursion, I must have the condition to stop this recursion, this terminating conditions that stops procedure from recursing endlessly, the recursive searches of endless loop. Recursive search, this is function represented the pseudocode of the function depth search. This is consists of the begin. If open is empty, then returns well. Current state is the first element of the open, because I will be moved from the first state of the open. If the current state is the goal, then it was successful and finish the procedure. Else, I will from the open, the tail of the open, because I will remove, and the head will remove the first one, that means head, and the closed with the current state added. I will put the removed from open and put in the closed. For each one of the current states, the current state in the open, when I take off from the open, this node will I explore its children for each one's current state. If not only closed or not, because when I reach or explore the node and get its children, for each children, if there is not exist in the open or the closed, I will put in the open. Not the closed order, then add the children to the front of open. And finally, their search, I will recursively recall the same function with the new parameters when I remove the nodes from the open and put it for the closed state or list. In this algorithm, there is no open list, because here is open list, but here I will implement the recursive, and I will remove the open from the algorithm. Now the new algorithm that representing the implementation of the recursive function will begin function that says reclosed by current state. Begin if current state is gone, okay, finish and successful. Add current state to the closed. While current state has an exam children, that means current state not empty. Begin child equal next and exam child. Now it means get another one. If child not member of closed, this was not found in the closed, then if the depth served child, that means recursive letters with the child. That means go to the same function with the current state will be the child, new child. This is recursive. If equal succeeds, that is not succeeds. And continue until I reach empty current state. If there is no goal, that means we can't fit. This is the representation or implementation of the recursive algorithm in this algorithm. Suppose we want to write an algorithm that determines whether a predicate calculus expression is a goal, is a logical consequence of some sets of assertion. This suggests goal-directed search with the initial query forming the goal and modus ponens defining the transition between states. Given a goal such as PA, for example, PA, the algorithm uses unification to select the applications whose conclusion match the goal. QX for PX, that's implied PX. Because the algorithms treat implications as potential rules for solving the query, they are often simply called rules. This is rule. After unifying the goal with the conclusion of the applications or rules and applying the resulting substitutions throughout the rule premise becomes a new goal. This is called sub-goal. I get from the goal, I get another conditions, implementing other conditions to get another new goal, and this new goal will become a new sub-goal. The algorithm then recurs and repeat this on the sub-goal. If the sub-goal match a part in the knowledge base, search terminates. The series of inference that lead to the four potential goals to given parts, proving the truth of the original. And this is representing the pattern-driven reasoning algorithms with the function pattern search. And this is algorithm. Now the subject of the production system. In the production system, I will present the definitions and history, and I will review examples of production systems and control of search in production system, and finally the advantage of production system for artificial intelligence. Now go to the definitions. The definition of production system. Production system consists of three parts. The first one is called the production rule. Production rule, there are often simply called productions. Productions is conditions and actions. Production rule consists of also two parts. The first one, conditions and action. That means FVM in the programming language. Two part, actions, conditions and actions, and written by rule. Actions imply condition, imply action, and thus conditions action based and defines a single chance of problem solving knowledge. Now the condition part of the rule is a pattern that determines when that rules may be applied to a problem instance, and the action part defines the association problem solving steps. Now the second part, the working memory. The working memory contains the descriptions of the current states of the word and the reasoning process. And this description or this expression is pattern that is matched against the condition parts of the production to select appropriate problem-solving actions. That means when the conditions elements of rule is matched, because this pattern and action, when this rule is matched by the contents of the working memory, the actions associated with the conditions may then be performed. The actions of production rules are specifically designed to alter the contents of working memory. And third part of production system, the recognize and act cycle. Recognize and act. That means implementing the rules with the conditions and actions. The control structure of the production system is simple. Working memory is initialized with the beginning problem. Describe patterns in working memory. These patterns are matched against the conditions of the production rules. This production subset of the production rules called the conflict sets. After I reaching the result of the conditions and actions, called conflicting set, and whose conditions match the patterns in working memory. The productions in the conflict sets are said to be enabled. One of the productions in the conflict set is then selected. That means conflict resolutions, and the production is fired. And to fire the rule, now if we want to fire the rule, its action is performed, changing the content of working memory. And after this action will be altering the content of this working memory. Now the conflict resolution chooses a rule from the conflict sets for firing. Conflict resolution strategies may be simple, such as selecting the first rule, which one I will select. This is the process of the selecting is the conflict resolution. First two conditions match the states of the rule, or may involve complex rules to selection heuristic. For example, production sets, I have three production sets. PA, that's mean AP, or CA imply AC, CP imply PC. These steps of iteration of this algorithm. Now, the working memory contains C, B, A, C, A. In this fashion, the complex set with the firing rule, the rules will be firing 1 or 2 or 3. That's mean 1, 2, 3. Because all this will be applied for this. Now, which one I will select? This firing, that is me selecting. I will select first one. The first rule, this PA. Now, after I fired one, PA equal AB, where is PA? This PA. Will be changed AB. Now, this is firing rule. After I selected one from the conflict set, I select firing rule 1. After applying this and altering the working memory, the changing this. After altering, that's become from PA become AP. Now CPA, CAP, and CA. Now from this, which one I will be used? From this PA, BA not found. CA, this CA and CA. Only two will find complete. Because there is one, I will find only one. That's two. Second rule. Second rule is CA. Now CA, AC. CA and CA will be changed to this AC. AC and CA will stay the same. Good? Now, for this, which rule will be filed or will be used? AC, there is no AC. CB, yes, CB. And BC, no. CA, yes. There is two rules. 2 and 3. 2 and 3. I will select one. First one. That's 2. 2. CA will be AC. CA will be AC and AC. AC be AC. Now, after altering the working memory, which rule will be applied for this? AC, no. CB, yes, CB, 3. Now, write the 3. And BA is first one. And AC, there is no one. Only two rules. Which one I would select? That's rule filed with only one. First one. One, what's this mean? One. BA change to AB. Where is BA? This BA. This will be AB. AC, AB, C. And these I will use only second rule. The CA, AC. CA, AC. Now implement become A, C, B, C. These only three. 3, CB, BC. CB with CBC. Now will be A, B, C, C. There is no rule will be implemented or this. This is final results. This is called the implementation of the simple production rule. Now we'll implement the production rule for the puzzles of the 8 puzzle. Now start states this and goal state this. Production state will be goal states in working memory holds and action. Black is not on the left edge. Move the blank left. That means if black is not on the left edge, move the blank left. And if blank is not on the top edge, move the blank up. If blank is not on the right edge, not here, move the blank right. Blank is not on the bottom, not here, here or here. Can I move the blank down? This is projection sets. Control regime. Try each projection in its order. Do not allow loops. Stop when goal is found. This is the condition. Now, the whole states of the problem states as like this. The end puzzle reached by projection system with the loop detection, and they found 5 from, and this is represent the implementation of the projection rule for the night tour problem. Now this is tour. How many places we can visit here? Only 8. Places. Now, for example, move 1, 8. For example, from 1 to 8. Or move 1 for 6. Or move 2 for 9. Move 2. For example, this is example. If he here, stay here. The night will be either in 6 or 8. Because here or like this. That means 6 and 8. When you were in 1, بيساعد أجاوب لما هو خلص يطلع إن شاء الله مستقبل. And this represents the rules and conditions and actions. Now, the protection system, for example, working memory either 1 and 2. Current square, and the goal square I want to reach 2. They stay in the 1, but I want to 2. Now, the complex set either rule 1 or rule 2. I will select 1. Select 1. Night on square 1 will be moved to night square 8. Now will become square 8. If you will square 8, there is 2 rules, 13 and 14. Either 3 or 1. I will select to move to the 3. When you will 3, I will select rule 5 and 6. 3 will move to 4 or 8. I will go to the 4 location, location 4. If the location 4, I will select 7 and 5. That means 8 and 9 or 3. I will select 9. 9 will be either move to square 2 or 4. I will select 2, and this is gone. This is a protection, implementing of protection rule for the night tour problem. And this is the present the flowchart of the implementing night tour problem in the protection system. And this is for sequence of the other protection system. And this is the same things for the problem. And this represents the flowchart of the, this is the present state examined, and this is state examined by backward search. This is forward, and this is backward search. This is the same. And this, we will finish this and continue on the next lecture. Thank you.